Hello students, welcome back to Future Foundation. Students, in this video probability, I will continue types of events and then I will discuss classical definition of probability. So let's start. So students, we have discussed 7 types in last video. Now in today's video, we will continue with 8th type and that is equiprobable events. So in this we will write equiprobable events are the events that have same likelihood of occurring, right? This means that each event in a set of equiprobable event has an equal chance of occurring. For example, tossing a coin or tossing a fair coin, getting heads or getting tails has a probability of 1 by 2, right? Same chance for heads as well as for tails, right? Now let's come to next type, that is mutually exclusive events. So in this we will write mutually exclusive events are the events that cannot occur simultaneously. That is, if one event occurs, it precludes the occurrence of the other. Means for example, rolling 3 and 4 simultaneously is not possible on a fair 6-faced die, right? Also, they are referred to as disjoint events, right? Okay, now let us take one more example. Say example 2. This was example 1 and this is example 2. On rolling a die, let A be the event of getting an odd number, right? That is, possible outcomes for having A would be 1, 3, 5, right? And B be the event of getting an even number. So possible outcomes for B would be 2, 4 and 6. Now we can see event A and event B are mutually exclusive, as we cannot have both events simultaneously, or we cannot have at the same time even and odd number, right? So A and B are mutually exclusive events. It implies what? It implies A intersection phi is a null set, right? Or A and B are disjoint events. Now let's come to next type, and which is exhaustive events. So in exhaustive events, we will write exhaustive events are a set of events when combined gives us a sample space, right? So if A1, A2, A3 and so on up to An are n events such that A1 union A2 union A3 union and so on up to union An is equal to S, then A1, A2, A3 and so on up to An are called what? Exhaustive events, right? So in total we have studied 10 types for events, right? Now let's come to the next topic of this video, which is classical definition of probability. So write down the heading, classical definition of probability. So in this we will write, if E be the event in which all outcomes are equally likely, or you can say all elementary events of that random experiment are equiprobable events, and let n be the total possible outcomes related to the sample space, out of which m are favorable to the occurrence of an event E. Then, according to the classical probability or classical definition of probability of an event E would be m by n, where m represents the number of outcomes favorable to an event E upon n represents number of total outcomes in sample space. So number of outcomes in sample space S, right? So in this whole chapter, we will use this formula for finding probability of an event, right? Also, as we know, range for M is from closed 0 to closed n, because n represents what? Number of outcomes favorable to E. So it can be 0 at lowest, or it can be n at highest. So M lies in between 0 and n closed. So if I divide both sides of this inequality by n, then we will have m by n from 0 to n by n, right? So m by n becomes 0 to 1, or m by n is nothing but p of e. So p of e lies between 0 and 1 closed. So as we have discussed, p of e is equal to 0 implies E is impossible event, right? And if P of E is equal to 1 implies E is sure event, right? Also let E bar be the event of not happening of event E, right? So probability of E bar would be n minus m by n, because in this case possible outcomes favorable to event E bar would be n minus m, right? Because m are favorable to event E. So for event E bar, which represents not happening of event E, would be n minus m. So P of E bar would be n by n minus m by n, or probability of E bar would be 1 minus probability of E, or probability of E plus probability of E bar is 1, right? And here E and E bar are the events which are mutually exclusive and exhaustive, right? Also here E and E bar are the events which are mutually exclusive and exhaustive, right? As we know, if two events are mutually uh, if two events are exhaustive, then their their sum of probabilities would be 1, because union of those events would give you sample space, right? And of course E and E bar are mutually exclusive as well, as they are disjoint. Now let's come to the question. Question is, if two dice are thrown, then probability of A getting some getting a doublet, and B, getting sum as 2, right? So in question it is given that we are rolling two dice simultaneously, right? So for this, sample space would be 1 1, 1 2, and so on up to 1 6, 2 1, 2 2, and so on up to 2 6, and so on up to 6 1, 6 2, and so on up to 6 6. Students, as you know, 1 1 represents 1 on first die and 1 on second die. 1 2 represents what? 1 2 represents 1 on first die and 2 on second die. Similarly, 6 6 represents, or 6 1 represents 6 on first die, 1 on second die, and 6 6 represents 6 on first die and also 6 on second die. So in total there are 36 sample points. So we can write n of s is equal to 36. Now let's say A be the event of getting a doublet. Also A be the event of getting the doublet. Doublet means outcome like 1 1, means same number on both dies. So 1 1 is a doublet. In the same way 2 2 is also the doublet, right? In the same way 6 6 is also the doublet. So in total, how many doublets are there? There are 6 doublets when we roll two dice simultaneously. So n of A would be 6. So probability of having a doublet is n of A by n of S, which is 6 by 36 and which is 1 by 6, right? Now, second part, this was part A. Now, let's come to part B. Part B is demanding for having sum as 2. Now, let B be the event of getting sum as 2, right? So for B, outcome would be 1 comma 1 only. In that case only we can have sum 2 if both dies have 1 and 1, right? No other possible case would be there. So implies n of p is 1. So probability of p would be 1 by 36. Now if we continue for having sum as 3 or 4, or now if we continue for having sum as 3 or 4 or 5 and so on up to 12, because 12 is the maximum sum both dice can have. If both dice have 6 and 6 on their faces, right? So if we continue, what we will have, let's say if we have a sum as 3, so in that case ordered or outcomes would be 1 comma 2 or 2 comma 1, right? Means first die has 1 and second die has 2, or first die has 2 or and second die has 1, right? So P of C, no, not P of C, it is N of C. N of C is 2, right? So in this case P of C is 2 by 36, right? So in the same way, if we have sum as 4, so D is 1 3, 3 1 or 2 2, right? So N of D would be 3. It implies P of D would be 3 by 36. right? Now, so what we are observing in these cases, that if we want sum for as 4, then we have outcomes as 3. If we want sum as 5, then outcomes as 4. If we want sum as 6, then outcome would be 5, like 2 4, 4 2, 3 3, 5 1, 1 5, right? Now if we have sum as 8, sum as 8, so in that case, let A be the event of having sum as 8, then outcomes would be 2 6, 6 2, 4 4, 5 3, 3 5, or any other case? No, not any other case. So in that case, P of A would be 5 by 36, right? So we are observing that up to 7, probability is increasing, or outcomes related to that event are increasing by 1. But after that, after 7, means from 8 to 12, outcomes are decreasing by 1, right? So if we are defining the probability of having sum as x, then probability would be x minus 1 by 36 when x is lying between 2 to 7, and this is 13 minus x by 36 when x is lying between 8 to 12 closed, right? So this is direct formula. You can find for any number from 2 to 12 by putting in this function, right? Now for this video we are done, students. Let's meet in next video. Till then, bye bye and take care.